So, last class we discussed Springs and Hooke's law for springs oscillating in one dimension. We considered a mass attached to a spring such that when pulled or pushed, it would experience a restoring force proportional to the elongation or the compression, and we let it freely oscillate. With this, we found the equations of motion. We then added a resistive force similar to that of air drag, that is, a force that is proportional to the velocity. In a similar way to that of the simple oscillator, we also found the equations of motion, considering the different regimes, depending on the values of the spring constant and the drag coefficient. We finally took a look at the forced oscillator. In particular, we looked at an oscillator that was subject to a time-dependent force, f of t equals a constant, multiplied by the cosine of omega t, where omega was the frequency of the oscillator. In particular, we found that if omega squared is equal to the spring constant k divided by the mass m, then the amplitude of the oscillation would become enormous, giving way to the phenomenon of resonance. So, this lesson, I will be giving a brief introduction to Lagrangian mechanics and its importance, and since it is quite a difficult topic, I will try to keep it short so that you can digest what has been said and the mathematical procedure. Now, the idea is really quite simple, but it does take some time to process it and get used to the ideas. So, I know that you will be anxious to see an example, but it will be quite difficult to fit it, at least in this lesson. So expect the example or the examples for the next class. In particular, I will give a brief overview of the calculus of variations. I will also talk somewhat on the importance of symmetries in physics and conservation laws. That is the heart and soul of physics nowadays, and this important result was proved by Emmy Noether, the first woman mathematician to hold a mathematics professorship at the University of Göttingen. Of particular importance is that the systems we will be considering obey Newton's laws of action and reaction, and that the forces are conservative. I will then use D'Alembert's principle to get to Lagrange's equations, and then I will give some definitions that will be important throughout our study of Lagrange's mechanics. We will first look at some basic properties of the calculus of variations and then an example. We will start by assuming we are living in a two-dimensional world such that we can only move in a plane. In this plane, each point can be characterized by its x and y coordinate. So one of the features of this world is that we have a function of x that can be written in terms of x, a function of x that we shall call y, and the derivative of this function with respect to x that we call y prime. Notice that this function f is a function of functions. The functions y and y prime are called functionals. That is, y and y prime are variables of the function f, but y and y prime are linearly independent functions themselves. Assume that now we choose 2 points in the plane and we want to travel from point 1 to point 2, and this path is not necessarily a straight line, but it can be a function of x, a function y of x. So as we travel along the path, we want to take the line integral from point 1 to point 2 along the path y of x of the function f that lives in this two-dimensional world. Even more, we want this integral to be in a stationary state. That is, j must be an extremum, a maximum, a minimum, or an inflection point. And we want to optimize f. Notice that since y and y prime are functions of x, this is effectively a one-dimensional problem. So our goal is to optimize the path of the function f that is represented by j, such that the path is given by y of x and we move from point x1 to point x2 where these points are fixed. They can be arbitrary, but they must be fixed. We will start by assuming that there is indeed a function y of x such that we can travel from point 1 to point 2 in a continuous and smooth way. Y of x is continuous and differentiable. Now, with this function y of x, we want to look into the neighborhood of the path for a modified function that satisfies the requirement that j is an extremum with respect to f. For this, we define a new function y of x that depends on a parameter alpha. That is, we assume that there is an arbitrary, continuous, and differentiable function eta of x that is added to the original path. This function eta is multiplied by a parameter that will make the overall value of eta larger or smaller, and we want to find what value of alpha makes the function eta take y of x to a value such that the path integral is an extremum. Thus, we extremize j with respect to alpha, not worrying about the specific form of eta of x. In our case, alpha would not depend on x, y, or any other function. That is, alpha is a constant variable, so to speak. Or, if you want to use more appropriate terminology, alpha is a global phase parameter. So, we want to extremize j with respect to the parameter alpha. For this, we take the derivative of the integral with respect to alpha and set it to 0. Since the integral is not with respect to alpha and alpha is effectively a constant, we can take the derivative inside the integral. We now use the chain rule, considering that x is the independent variable. We also notice that y of x and y prime of x are the functional variables, so that the chain rule can be applied to both variables. The integral that remains can be split into two terms. The term involving y prime can be integrated by parts. The integral by parts is quite simple, considering that y prime is the partial derivative with respect to x. Notice that when we solve the integral, we are left with a term that depends on the endpoints. Since we are considering that the endpoints are fixed, the variation with respect to alpha is 0, so that term goes to 0 and we are left with a term that we can replace back in the integral expression. In this integral, we can factor out the derivative of y with respect to alpha. Since the derivative of y with respect to alpha cannot always be 0, then the term in parentheses must be 0. We will not formally justify the reason, but it can be seen why this is the case. Thus, the differential equation to find the appropriate optimized function y of x is given by this final expression. It is important to notice that this procedure gives a formula to solve for y of x, not f of x or f of y or something of the sort. This equation we just examined is important since it's related to Hamilton's principle and classical mechanics. It is important to remark that we have not said anything about physics yet. This has been a purely mathematical approach and can be used for problems outside of physics. However, we are now going to apply it to a physics problem. We will now look at an example of how to use the variational principle in physics. In this example, we will obtain Snell's law using Fermat's least time principle. Fermat was a pre-Newtonian mathematician, meaning he didn't have notions of calculus. So this is the modern approach to solving this problem. The idea is that we shine a ray of light, initially in a medium where the speed of light is v1, into a flat surface such that the speed of light changes to a speed v2. In principle, v2 can be greater, smaller, or equal to v1. We want to see how much the path changes. Now, Fermat, unlike other scientists of his time, determined that the path that the light follows is that of minimal time to get from one point to the other. Notice that this does not necessarily imply straight lines, but we will get this result for the geometry we are considering. We will also consider we are in a two-dimensional setting. Of course, this can be done in a three-dimensional setting, but the result will not change. So we set up the integral considering that it is time we want to extremize. That is a function of the path. Notice that we are extremizing, meaning that as time can be a minimum, it can be a maximum or an inflection point. However, due to the nature of the problem, we will get a minimum. Also, notice that we must write the time it takes to get from one point to another in terms of the path taken, since it is the path the one we want to extremize. We will split the integral into two parts, one in the first medium and the other one in the second medium. Now that we have done this, the question is, well, now what? Since both paths are different, one good way to distinguish them is to name the variables differently. Writing this in terms of the path length is somewhat cumbersome, so we can factor out dy1 and dy2 so that it is more clear which one is the integration variable. Notice that we use the dy terms as our independent variables so that the geometry of the problem matches that of Snell's law. Of course, we can use the dx terms as our independent variables, but it would take one more step. We now write dy1 in terms of dy2, so we can place both terms under the same integral. Also, notice the negative sign that comes out. Now we can extremize, that is, minimize, in this case. To extremize, we will start by noticing that there are two functionals, the derivative of x1 with respect to y1 and the derivative of x2 with respect to y1. Thus, the function to optimize is given in terms of y1, the two functionals x1 and 2 of y, and the derivatives of the functionals with respect to y1. You can easily see that the optimization yields taking the explicit derivatives gives now, using the picture again, we see that 1 divided by the speed of light in the first medium, v1, times the sine of the incident angle minus 1 divided by the speed of light in the second medium, that is v2, times the sine of the refraction angle, is a constant. This constant must be obtained from physical conditions. If the speed of light is the same in both mediums, then the angles must be the same and the constant is 0. This way, we can rearrange the equation and multiply both sides by the speed of light in vacuum, that is c, to obtain Snell's law. Also, remember that n is the refractive index, that is c divided by the speed of light in the medium.